Good day, I'm Jonah McLeod, and joining me is SimplEx Micro founder and CTO Dr. Thang Tran, best known as the architect of the RISC-V vector processor shipping in the Meta MTIA chip. In episode 5, the conversation was around benchmarking the performance model. Episode 6 walks through how the performance model works, how it evolved toward cycle-accurate realism, and why configurability and custom RISC-V instructions matter for real-world hardware software co-design. To begin, how do your performance model concepts differ from traditional approaches?
The, the performance model algorithm is actually the same as my dissertation back in 1990. Each instruction have a perfect view of the execution and related resource of all earlier instruction in the pipeline. Each instruction will walk through the execution pipeline until completion and retire before the next instruction can start. And basically one instruction at a time. It is a perfect vision of everything in the past and in the future, in which you cannot do in RTL. For example, the future event of cat hit and miss is not known for the load store operation in RTL, but for the performance model, it is, we get all that information.
What are the key steps you follow to evolve the performance model from a broad initial design to a more accurate, detailed one?
So in the stage one, the initial design of the performance model does not have any buffer or queue. A store instruction assumes that it will take an entry in the store buffer because we look at one instruction at a time. So there's no such thing as a store buffer. There is no limitation in the number of entry. In stage two, the performance sensitivity analysis will be done by recording the number of valid entry for the store buffer in each cycle into a Gaussian distribution graph. And then we make a decision on what that store buffer size will be. And the same analysis is done for all other buffers and queues. Unfortunately, we cannot choose to maximize the maximum size for all the buffers and queues. We must analyze the impact on the actual buffer size. The actual buffer size will be used for both the RTL and the performance model. And we expect that the performance numbers will be better correlated.
What additional capabilities do you plan to incorporate into the performance model?
So in stage two, we'll also design more accurate L2 cache and VPU. The L2 cache will become real. It is a larger version of the L1 cache by just changing the cache sizes, the way associative, the cache organization, and the latency time. As time go on, we will also add AXI, CSI bus protocol, and model the HBM, the high bandwidth memory. We currently have a very good performance model for the VPU, but we are planning to redesign some of the function to closely correlate with the RTL, cycle by cycle correlation for the VPU.
What additional features do you consider essential for a robust and useful performance model?
There are three considerations. First is the tools. If we plan to provide the customer the performance model for hardware software co-design, then the compiler, the instruction set simulator, and the Linux version must be all open source, so it can be used by any customer. Second is the configurability and the portability. We do not use any fixed number in the design. All parameters are declared in the define.h file, which can be shared between the RTL and the performance model. The instruction decode tables are also shared between the RTL and the performance model. So this configuration can be changed for either or both at the same time with the ease of the performance correlation. The third is the customization. Both RTL and performance model are designed with the what if in mind. For custom instruction, if we add another custom instruction decode table or the number of execution queue and the number of functions unit can be changed from 8 to 9 or from 8 to 10. The what if must be a simple process.
Why do you believe custom instructions play such an important role?
This is the main advantage of RISC-V over ARM or x86 instruction set. The RISC-V ISA sets aside a number of opcode spaces for custom instructions. The custom instruction provide customer with many advantages, a hardware acceleration, functional unit to improve the performance, adapted specially for their application codes. Security, no one else can reproduce the RTL without knowing the custom instruction. And all this can be done with the performance model before imported it into the RTL.
All right. Thank you. And we'll see you next time on Conversation with the CTO.